Hey everyone, let's just jump right into today's explainer. We're going to explore something super fascinating: how we're finally teaching autonomous AI agents to build true lifelong memory systems. I mean, we've all been there, right? You're talking to an AI, it seems incredibly smart for the first 5 minutes, and then boom, it completely loses the plot. Well, today we are unpacking the cutting-edge architectures that are fixing this dreaded memory wipe once and for all. But to really understand the solution, we first have to ask a crucial question. Why do basic AI agents fail in production? See, when agents rely on basic vector storage, which is really just a fuzzy search engine for data, they inevitably lose context and break down in the real world. It's a pattern that literally kills most production rollouts. The underlying models, they've gotten exceptionally good at reasoning, but reasoning without the right context, that's just an expensive hallucination. And when memory scales up, flat vector databases cause these agents to fail in four pretty spectacular ways. First up, context poisoning. This is where agents actually retrieve their own past hallucinations and end up reinforcing their own errors. Yikes. Second is context distraction, where they just drown in semantically similar but totally irrelevant noise. Third, context clash. Imagine retrieving two contradictory facts simultaneously, like an old and a new shipping address. The agent just ends up guessing. And finally, work duplication. This one is a total fatal flaw in multi-agent systems. Picture a manager agent, or research agent, and a coding agent trying to pull off true agent collaboration. Without a shared memory state for communication and coordination, they completely lack distributed intelligence. So Agent A fetches data, Agent B fetches the exact same data. Without memory-driven conflict resolution, your whole system is just burning tokens on redundant tasks. No good. So to figure this out, researchers looked at the biological blueprint, specifically using human memory as a model. To solve the context crisis we were just talking about, researchers basically mapped AI to four distinct biological categories. You've got working memory, that's the immediate context window. Then there's episodic memory, which stores specific past experiences and temporal sequences, so the agent actually remembers what happened yesterday. Then we have semantic memory, which serves as a persistent knowledge base of facts. And finally, procedural memory, which acts as the automation engine. This is exactly how a planner agent handles task delegation or how worker agents encode action sequences. Treating all these the same is a massive mistake because each one requires completely different access patterns and persistence rules. But here's the real kicker. Even if you categorize everything perfectly, semantic similarity alone totally fails at scale. Imagine asking a worker agent about a specific shipping delay from, say, 3 weeks ago. A flat database might return 10,000 results just because they contain the word shipping. So the agent is still drowning in similar but totally irrelevant results. That brings us to hierarchical routing and page error. So how does this actually build into a real solution? Well, by organizing memory into layers, think domains, categories, and episodes, systems like HMEM can route queries precisely without exhaustively scanning the entire database. It's exactly like a giant filing cabinet. Instead of reading every single piece of paper to find what you need, you just check the drawer label, then the specific folder, and then the document. This index-based routing provides truly scalable precision. Expanding on that idea, it's brilliant how systems like MemGPT or Letta treat memory just like a computer operating system. So instead of the agent just being a passive recipient, a dedicated memory agent actively pages information back and forth between a massive external archive and the immediate working core context. It gets to decide what to keep close and what to archive, which saves you a massive amount in API costs while giving the illusion of infinite memory. It's a real game changer. Let's move on to using knowledge graphs for exactness. Now you might be wondering, how do we solve precise factual grounding in high-stakes domains, places where fuzzy guesses are downright dangerous? Well, vector similarity might just tell you, drug X treats hypertension, which seems helpful, right? But a knowledge graph uses multi-hop reasoning to traverse the exact relationships. It connects the dots to realize, wait a minute, drug X actually interacts lethally with the patient's other medications. Therefore, the agent explicitly knows to recommend drug W instead. You simply cannot get this kind of verifiable safety from a flat vector database. For a medical assistant or, say, an evaluator agent reviewing code compliance, GraphREG provides absolute transparency. If a critic agent challenges a conclusion, the system provides exactness through explicit nodes and edges for perfect conflict resolution. Vector systems, they just offer fuzzy approximations. But if an agent needs to justify its conclusions by citing a verifiable chain of facts, graph architectures provide that explicit proof. Which leads us to consolidation and the fact that agents actually need sleep. The absolutely crucial point here is that agents, much like us humans, accumulate way too much noisy episodic data over time and desperately need a mechanism to consolidate it, to forget the noise and keep the lessons. This is handled beautifully by the active dreaming memory architecture. In the online wake phase, the agent is interacting with its environment, doing its daily tasks, and collecting raw episodic traces of everything that happens, including all its mistakes. Then it enters an offline sleep phase.
During this offline sleep cycle, a reflector module clusters the failures, like, say, hitting an API timeout multiple times. Then, a dreamer module actually generates counterfactual scenarios, simulating what it should have done. It consolidates these into verified semantic rules, meaning your agent wakes up having actually learned from its experiences, ensuring it never makes that same frustrating error twice. It's honestly amazing.
And this isn't just theory. By converting episodic failures into semantic rules through dreaming, this architecture achieves a stunning 83% average accuracy across multi-domain benchmarks. It heavily outperforms baselines that lack consolidation, proving that just replaying raw memories isn't enough. Agents literally need to process and verify their memories offline to truly learn. Next, let's look at production memory frameworks. So, how are leading tech companies actually putting these theoretical architectures into production today? Well, there is no one-size-fits-all. You have to choose the framework that fits your specific workload. In a multi-agent system where, for example, a manager agent delegates to a reviewer or critic agent, frameworks like Letta offer native agent collaboration boundaries. This means they can share distributed intelligence without polluting each other's state. Or maybe you need Memo for personalizing a consumer chatbot. It all depends on the goal. Just look at the numbers. When asking an agent what was decided in a meeting 3 weeks ago, architecture is quite literally everything. Zep's temporal knowledge graph actually outperforms standard hybrid stores like Mem0 by nearly 15 points on the long Memaville benchmark, 63.8% versus 49%. How you structure memory directly dictates how smart the agent appears over time. But here is the reality check for the enterprise, the governance gap. Who owns the memory? While these memory frameworks are great for remembering conversations, they completely lack the enterprise governance, audit logging, and data lineage needed for corporate data estates. If an autonomous financial agent makes a trade, you need absolute certainty to know exactly what source data it used. You can't just have a black box where nobody knows who owns the data or why a specific decision was reached. To solve this enterprise gap, companies wrap these memory frameworks in a context layer, like Atlan. This grounds the AI in authoritative business logic. It provides cross-system entity resolution, operational playbooks, and active metadata, ensuring the agent isn't just remembering a chat, it is operating on the verified, trustworthy reality of your company's data. So what does this all mean for us? As we move from forgetful single-turn bots to autonomous, hierarchical, multi-agent systems that sleep, dream, and consolidate lifelong memories, just think about the possibilities. What complex workflows will you delegate to a team of AI agents that finally remembers everything you've ever taught them? It's a truly fascinating future. Thanks for joining me on this explainer, and I hope this sparks some new ideas for you. Keep learning.